Tonight, we turn our gaze upward towards something so familiar that we often forget to truly see it. That hazy ribbon of light stretching across the darkness has been there for as long as humans have had eyes to wonder. It has been called a river of stars, a path for spirits, a road to the heavens. The ancient Greeks looked up and saw spilled milk. The Romans called it Via Lactea. We know it simply as the Milky Way. And here is what makes this particular subject so remarkable. When you look at that band of light on a clear night, you are not looking at something distant and separate from yourself. You are looking at your own galaxy from the inside. You are seeing the accumulated glow of billions of stars that share this vast structure with our sun, with our small planet, with you. Every mythology that ever tried to explain that ribbon was, in its own way, trying to understand home. This is the story of that home, not as a static address in the cosmos, but as a living thing, shaped by collisions and cannibalism, held together by forces we cannot see, and moving toward a future we are only beginning to understand. By the time you reach the end of this journey, you will know where we are, how we got here, and where we might be going. And perhaps, along the way, you will find it easier to drift into sleep, carried by the slow turning of 200 billion stars. The story begins, as so many astronomical stories do, with someone looking more carefully than anyone had looked before. In the year 1610, while William Shakespeare was completing his final plays in England, an Italian mathematician named Galileo Galilei pointed a new instrument toward the night sky. The telescope was not his invention, but he had improved it considerably, and he understood that it might reveal things the naked eye could never see. When Galileo turned his telescope toward the Milky Way, he discovered something that changed humanity's understanding of the cosmos. That smooth, milky band of light was not a cloud, not a celestial river, not the breath of a goddess. It was composed of countless individual stars, so numerous and so faint that the eye blended them into a continuous glow. Where people had seen unity, Galileo revealed multitude. The heavens, it seemed, were far more crowded than anyone had imagined. This discovery raised a question that would take another 3 centuries to answer. If the Milky Way was made of stars, and if our sun was itself a star, then what exactly was the relationship between them? Were we inside this structure, or outside it? Was the Milky Way the entire universe, or merely one piece of something larger? For more than 300 years, the most brilliant minds in astronomy assumed that what Galileo had seen was, in fact, everything. The Milky Way was the cosmos, and the cosmos was the Milky Way. Toward the end of the 18th century, a German-born musician who had become one of England's greatest astronomers attempted the first systematic survey of our stellar surroundings. William Herschel counted stars in different directions across the sky, reasoning that he could map the shape of the universe by seeing where the stars were most and least concentrated. His conclusion was that we lived inside a flattened disk of stars, something like a grindstone, with the sun positioned somewhere near the center. He was partly right about the shape, though dramatically wrong about our location within it. By the early 20th century, astronomers had identified strange spiral-shaped patches of light scattered across the sky. They called these objects spiral nebulae, assuming they were clouds of gas and dust within our own stellar system. Some were enormous and bright, like the great nebula in Andromeda. Others were small and faint. The question of what they actually were became one of the most contentious debates in the history of science. In April of 1920, two American astronomers faced each other at the Smithsonian Museum of Natural History in Washington to argue opposite positions on what became known as the Great Debate. Harlow Shapley, who had recently shown that the Milky Way was far larger than previously thought, insisted that these spiral nebulae were minor features within our galaxy. Heber Curtis argued the opposite, that they were island universes, galaxies in their own right, separated from us by unimaginable distances. The evidence at the time was ambiguous, and the debate ended without a clear winner. But the answer was coming, carried by light that had been traveling for more than 2 million years. Edwin Hubble arrived at the Mount Wilson Observatory in California in 1919, just as the largest telescope in the world was being completed. The 100-inch Hooker telescope could gather more light than any instrument before it, revealing objects that had been invisible to earlier generations of astronomers. Hubble, a former lawyer and athlete who had reinvented himself as an astronomer, set out to solve the mystery of the spiral nebulae once and for all. His method relied on a discovery made a decade earlier by a woman who never received the credit she deserved. Henrietta Swan Leavitt worked at the Harvard College Observatory as a human computer, a term used at the time for people who performed tedious calculations and measurements. While studying photographs of a small companion galaxy called the Small Magellanic Cloud, Leavitt noticed something remarkable about a class of pulsating stars called Cepheids. The brighter they were, the longer they took to complete one cycle of brightening and dimming. This period luminosity relationship meant that if you could measure how quickly a Cepheid pulsed, you could calculate its true brightness. And if you knew its true brightness, you could determine how far away it was by comparing that to how bright it appeared. Hubble spent years photographing the Great Spiral Nebula in Andromeda, searching for Cepheid variables among its stars. By the end of 1924, he had found 12 of them. When he applied Leavitt's method, the result was staggering. The Andromeda Nebula was not a cloud within the Milky Way. It was a separate galaxy, located roughly 900,000 light-years away. This estimate was actually too low. We now know the true distance is about 2.5 million light-years, but even the smaller number placed Andromeda far beyond the borders of our own galaxy. Hubble wrote a letter to Harlow Shapley informing him of the discovery. According to those who were present, Shapley read the letter and remarked, "Here is the letter that has destroyed my universe." The universe had not been destroyed, of course. It had expanded suddenly and dramatically in the human imagination. What had seemed to be the entire cosmos was revealed to be a single galaxy among countless others. The Milky Way was not everything. It was home. Let us take a moment now to consider what we actually know about this home of ours. If you could somehow travel outside the Milky Way and look back at it from a great distance, what would you see? You would see a disk. Not a perfect, flat disk like a dinner plate, but a disk that has been bent and warped slightly, like a vinyl record left in a warm car. The disk stretches approximately 100,000 light-years from edge to edge, though recent studies suggest it may extend even farther when you include the faintest outer structures. At its thickest point, in the central bulge, it measures perhaps 12,000 light-years from top to bottom. But in the spiral arms, where we live, the disk is remarkably thin, only about 1,000 light-years thick. If you scaled the Milky Way down so that its diameter matched the width of a football field, the thickness of the disk in the spiral arms would be roughly the width of a sheet of paper. At the center of the disk, you would see a bright, elongated bulge of older stars glowing with a warm yellowish light. This bulge is not spherical, but bar-shaped, extending outward from the core and serving as the anchor point for the spiral arms. The Milky Way is what astronomers call a barred spiral galaxy, one of the most common types in the universe. Extending from the ends of that central bar, two major spiral arms wind outward through the disk. These are the Scutum Centaurus arm and the Perseus arm, the Milky Way's primary structural features. Between and around them, smaller arms and spurs create the complex branching pattern that gives spiral galaxies their distinctive appearance. The spiral arms are not solid structures that rotate together like the spokes of a wheel. They are waves of density, regions where gas and dust are compressed, triggering the formation of new stars. Stars enter the arms, spend time in the crowded conditions, and eventually move on, like cars passing through a traffic jam. Our Sun is located in one of the smaller structures, a region called the Orion Arm, or sometimes the Local Arm. It sits about 27,000 light-years from the galactic center, roughly halfway between the core and the outer edge. Picture yourself on a beach, looking out at the ocean. If the galactic center is the distant horizon, we are standing about where the waves begin to lap at your feet. Not at the center of things, but not at the farthest margins either. We occupy a kind of cosmic middle ground. The Sun is not standing still in this structure. It is moving, quite rapidly by human standards, at about 220 kilometers per second as it orbits the galactic center. At that speed, you might expect the orbit to be completed quickly, but the distances involved are so vast that one complete trip around the galaxy takes approximately 250 million years. This period is sometimes called a galactic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 18 or 19 of these immense circuits. During the Sun's most recent orbit, dinosaurs walked the Earth for most of the journey, appearing about 230 million years ago and disappearing about 66 million years ago. Our entire recorded human history, all of civilization, all of the written word, has occurred within a small fraction of a single % of one galactic year. If you have ever looked up at the night sky and felt impossibly small, you understand why these numbers matter. The Milky Way contains somewhere between 200 billion and 400 billion stars. The uncertainty in that number is itself enormous, spanning a range of 200 billion. But even the lower estimate is difficult to comprehend. If you tried to count those stars at a rate of 1 per second, without sleeping or taking breaks, it would take you more than 6,000 years to finish. Among those hundreds of billions of stars, only one is ours. The Sun is an ordinary yellow dwarf star, neither particularly large nor particularly small, neither unusually bright nor unusually dim. In nearly every measurable way, it is average. This ordinariness, far from making us insignificant, is what makes life possible. A more massive star would burn through its fuel in millions of years rather than billions, not leaving enough time for complex life to evolve. A smaller star would be cooler and dimmer, requiring planets to orbit so close that they might become tidally locked, with one side in permanent daylight and the other in permanent darkness. The Sun's position within the Milky Way may also be significant, though this idea remains somewhat speculative. We are located between the major spiral arms, in a relatively quiet neighborhood with fewer nearby stars and less intense radiation than the dense star-forming regions deeper in the arms. Some researchers have suggested that this position, combined with our distance from the galactic center where activity is more intense, provides a kind of habitable zone not just for planets around stars, but for stars within galaxies. The conditions that allowed life to develop on Earth may depend not only on where our planet orbits within the solar system, but also on where our solar system orbits within the galaxy. Looking around our immediate cosmic neighborhood, we find ourselves surrounded by familiar objects. The constellation Orion, one of the most recognizable patterns in the Northern Hemisphere winter sky, is named for the arm of the galaxy in which we reside. Many of its brightest stars, including Betelgeuse and Rigel, are our neighbors within this spiral arm. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery where new stars are being born right now, only about 1,300 light-years away. When you look at that nebula on a winter night, you are seeing our own small corner of the galaxy in the act of creation. Now we turn our attention inward, toward the center of the galaxy, where something waits in the darkness. For most of human history, the galactic center was invisible to us, hidden behind vast clouds of interstellar dust that block visible light. These dust clouds are so thick that if you tried to look toward the center with your eyes alone, you would see nothing but darkness, a seemingly empty region in the direction of the constellation Sagittarius. Only in the 20th century, when astronomers began observing the sky in radio waves and infrared light, did the true nature of the galactic center begin to reveal itself. What they found was chaos and wonder in equal measure. The innermost region of the Milky Way is crowded with stars, millions of them packed into a space only a few light-years across. Gas clouds whip around at tremendous speeds, heated to millions of degrees. Magnetic filaments stretch for hundreds of light-years, their origins not fully understood. And at the very center of it all, there is a point of intense radio emission that astronomers named Sagittarius a star. For decades, scientists suspected that this radio source marked the location of a supermassive black hole, an object so massive that nothing, not even light, could escape its gravitational pull. But suspicion is not proof, and proving the existence of something that cannot be directly observed required extraordinary patience and ingenuity. Two astronomers, working independently on opposite sides of the world, dedicated their careers to finding that proof. Reinhard Genzel, working with telescopes in Chile, and Andrea Ghez, working with the Keck Observatory in Hawaii, spent years tracking the motions of stars near the galactic center. These stars are moving not gently and slowly, like the Sun in its orbit, but at tremendous velocities, some exceeding thousands of kilometers per second. By plotting their paths over many years, both teams demonstrated that the stars were orbiting an invisible point, something with a mass of about 4 million suns compressed into a space smaller than our own solar system. One star in particular, designated S2, completed an entire orbit during the period of observation. Its path was a perfect ellipse, the kind of orbit predicted by gravity alone, with the invisible mass at one focus. The precision of the measurements was breathtaking. Genzel and Ghez, along with theoretical physicist Roger Penrose, were awarded the Nobel Prize in Physics in 2020 for proving that this object could only be a black hole. But even a Nobel Prize did not provide an image. For that, astronomers needed to build a telescope the size of the Earth itself. The Event Horizon Telescope is not a single instrument, but a network of radio observatories scattered across the globe, from Hawaii to Spain, from the South Pole to the mountains of Chile. By coordinating their observations with atomic clocks and combining their data using sophisticated algorithms, these observatories function together as a single telescope with an effective diameter of nearly 13,000 kilometers. It is the highest resolution imaging instrument ever created, capable of seeing details at the center of our galaxy that no other telescope could resolve. In April of 2017, the Event Horizon Telescope turned its attention to Sagittarius, a star. For 4 days, 8 observatories on 6 continents recorded radio waves from the galactic center, generating about 5 petabytes of data, so much that it was faster to physically fly the hard drives to the processing centers than to transmit the information over the internet. Then came years of analysis, as scientists developed new methods to process the data and extract a meaningful image from the noise. On May 12, 2022, the result was revealed to the world. The image showed a dark central region, the shadow of the black hole's event horizon, surrounded by a bright ring of glowing gas. This was not a photograph in the traditional sense, but a reconstruction based on radio observations, showing the radio emissions from material heated to billions of degrees as it spirals toward the point of no return. The black hole itself remains invisible, as it must. What we see is its influence, the light from matter falling forever toward a boundary from which nothing returns. The dark circle at the center of the image is about the size of Mercury's orbit around the Sun, yet it contains the mass of 4 million stars like ours. The numbers here are, frankly, absurd. If you compress the Sun to form a black hole, it would be only about 6 kilometers across. Sagittarius, a star, is about 12 million kilometers across. It is small by cosmic standards, small enough to fit comfortably inside Mercury's orbit, yet it anchors our entire galaxy. Let that settle for a moment. There is no rush. Everything in the Milky Way orbits around this dark heart, including our Sun and all its planets. We are moving at tremendous speed through the galaxy, yet we will never fall into the black hole at its center. We are too far away, held in a stable orbit by the same principles that keep the Earth circling the Sun. The supermassive black hole is a gravitational anchor, not a cosmic drain. It shapes the galaxy without consuming it, a quiet presence at the center of things. And yet, the black hole may not always have been so quiet. There is evidence that Sagittarius A star has had more active periods in the past, episodes when large amounts of gas fell into its vicinity and were heated to such extreme temperatures that they radiated powerfully across the electromagnetic spectrum. These outbursts may have cleared gas from the central regions of the galaxy, influencing star formation for billions of years. The black hole, for all its current quietude, has shaped the evolution of our galaxy in ways we are only beginning to understand. It is also possible, though not certain, that the black hole has grown through mergers with other black holes. When galaxies collide and merge, their central black holes eventually spiral together and coalesce, producing gravitational waves that ripple through space and time. The Milky Way has consumed other galaxies throughout its history, and each of those galaxies may have contributed its own black hole to the central object we observe today. The 4 million solar masses we measure now may be the accumulated remnants of many smaller dark hearts collected over 13 billion years of cosmic history. This brings us to a chapter in our story that was almost entirely unknown until very recently. The history of the Milky Way is not a history of solitary evolution. It is a history of collisions, mergers, and cosmic cannibalism. The Gaia spacecraft was launched by the European Space Agency in December of 2013 with an ambitious goal: to create the most precise three-dimensional map of our galaxy ever made. Over the following years, Gaia has measured the positions, distances, and motions of nearly 2 billion stars in the Milky Way. It is, in effect, creating a movie of the galaxy, showing not just where stars are, but where they are going. When astronomers began analyzing Gaia's data, they found something unexpected. Among the billions of stars in the survey, roughly 30,000 seem to be moving the wrong way. While most stars in the solar neighborhood orbit the galactic center in the same direction and at similar speeds, these 30,000 stars were following different paths, moving in elongated orbits that take them plunging through the disk and then looping far out into the halo. Their chemical composition was also different from typical Milky Way stars, containing fewer heavy elements and showing patterns characteristic of a different stellar population. These stars, the astronomers realized, were not born here. They were immigrants, the remnants of another galaxy that collided with the Milky Way billions of years ago. The discovery was announced in 2018 by a team led by astronomer Amina Helmi at the University of Groningen. They named the long-dead galaxy Gaia Enceladus after the mission that revealed it and a giant from Greek mythology who was the offspring of the primordial goddess Gaia. Other researchers independently discovered the same structure and gave it a different name, the sausage, based on its distinctive shape in certain orbital diagrams. Today, the collision is often referred to as the Gaia sausage Enceladus event, awkwardly combining both names. The collision happened approximately 10 billion years ago, when the Milky Way was young and still forming. Gaia Enceladus was not a small galaxy, at least not by the standards of the objects that would later orbit the Milky Way as satellites. It contained perhaps 500 million stars and a significant amount of dark matter. When it fell into the young Milky Way, the impact was catastrophic. The orderly disk that had been forming was disrupted, heated, and puffed up into what we now call the thick disk. Many of the globular clusters that orbit the Milky Way today, ancient spheres of hundreds of thousands of stars each, were likely captured during this collision, and the intruder was destroyed, its stars scattered and absorbed into the structure of our growing galaxy. This was not the only ancient collision. Using the same Gaia data, astronomers have identified other streams of stars that appear to be the remnants of separate merger events. In 2024, researchers announced the discovery of two ancient stellar streams named Shakti and Shiva, after the Hindu deities whose union created the universe. These streams are more than 12 billion years old, dating to a time before the Milky Way had even developed its spiral arms and disk. They may be among the original building blocks from which our galaxy was assembled. The picture that emerges from these discoveries is startling. The Milky Way did not form in isolation, gradually condensing from a primordial cloud of gas. Instead, it grew through a process of hierarchical assembly, consuming smaller galaxies and incorporating their stars into its own structure. The merger with Gaia Enceladus was the most significant of these events, but it was not unique. Our galaxy is, in a very real sense, a collection of ghosts. If you could rewind the history of the Milky Way and watch it unfold in fast motion, you would see something like a slow-motion feeding frenzy. Small galaxies fall in from all directions, are torn apart by tidal forces, and have their stars incorporated into the growing structure. Larger galaxies collide with enough force to reshape the disk, triggering bursts of star formation and scattering debris across the halo. Through it all, the Milky Way grows larger and more massive, an accumulation of captured light. The feeding has not stopped. At this moment, the Milky Way is in the process of consuming at least one small galaxy and may be interacting with several others. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994, is the most prominent example. Located on the far side of the Milky Way from our position, this small galaxy has been making repeated passes through our galactic disk for billions of years. Each pass strips away more of its stars and brings it closer to complete dissolution. The stream of stars trailing behind it can be traced across much of the sky, a river of light marking the path of destruction. The Sagittarius Dwarf may have done more than simply donate its stars to the Milky Way. Simulations suggest that its repeated passages through the disk have sent ripples through the structure of our galaxy, like the waves created when a stone is dropped into water. These ripples may have triggered bursts of star formation at specific times in the past, and some researchers have suggested, though this remains speculative, that one such burst may have coincided with the formation of our own sun about 4.6 billion years ago. If true, we might owe our existence to a galactic collision that happened billions of years before the Earth was formed. Stay with me here, because what comes next is remarkable. We have spoken of stars, of black holes, of ancient collisions, but we have not yet addressed the most fundamental question about the Milky Way, the question that touches the deepest mysteries in physics. What is our galaxy actually made of? If you added up all the mass in the Milky Way's stars, gas, and dust, you would get a number somewhere around 100 billion solar masses. This is an enormous amount of matter by any reasonable standard. It represents 200 billion or more stars, vast clouds of hydrogen and helium, planets and asteroids and comets beyond counting, and perhaps 1 trillion worlds we will never see. And yet, it is only a small fraction of the Milky Way's total mass. When astronomers measure the mass of our galaxy by studying the motions of stars and gas, they find something troubling. Objects at the outer edges of the galaxy are moving too fast. If the mass we can see were the only mass present, these outer objects would have flown off into intergalactic space long ago, like water droplets flung from a spinning wheel. The fact that they remain bound to the galaxy tells us that there must be additional mass that we cannot see, providing the extra gravity needed to hold everything together. This invisible mass is what we call dark matter. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. We cannot detect it directly with any instrument we have built, and yet it makes up approximately 85% of the matter in the universe and accounts for most of the Milky Way's mass. The best current estimates suggest that the Milky Way's total mass is about 1.5 trillion solar masses. Of this, only a few percent is in the form of stars and gas that we can observe. The rest is dark matter, arranged in a vast, diffuse halo that extends far beyond the visible disk and spiral arms. If you could see dark matter, you would find that the bright, beautiful galaxy we photograph is just a small, luminous core embedded in an enormous sphere of invisible substance. Recent research has revealed that the dark matter halo is not even spherical. Observations from the Gaia satellite have shown that the stellar halo, the sparse population of stars that floats above and below the galactic disk, is tilted and elongated, shaped more like a football or a zeppelin than a perfect sphere. Astronomers now believe that the dark matter halo has the same shape, and that this tilted, football-shaped envelope is responsible for one of the Milky Way's most puzzling features: the warp. The Milky Way is not perfectly flat. At its outer edges, the disk bends and flares, warping upward on one side and downward on the other, like a record album that has been twisted slightly. Radio astronomers first detected this warp in the 1950s by mapping clouds of hydrogen gas, but for decades no one could explain what caused it. The gravity of the Magellanic Clouds, the Milky Way's largest satellite galaxies, seemed like a possibility, but calculations showed they were not massive enough to produce such a pronounced distortion. The answer, it now appears, involves dark matter. If the dark matter halo is tilted relative to the disk of visible stars and gas, then the disk feels an uneven gravitational pull, stronger on one side than the other. Over time, this asymmetric force causes the disk to warp and oscillate, bending in exactly the way we observe. The invisible structure of our galaxy, the part we cannot see, is shaping the part we can. This is the kind of detail that keeps astronomers awake at night. Ironic, given our purpose here. The Large Magellanic Cloud, one of those satellite galaxies we mentioned a moment ago, is itself swimming through this ocean of dark matter. As it moves, it creates a wake, like a ship ploughing through calm water. This wake was predicted by computer simulations and then confirmed by observations of stars in the halo. We can see the disturbance caused by something we cannot see, moving through a medium that is itself invisible. The universe is showing us its hidden structure through secondary effects, through hints and echoes and gravitational whispers. There is still so much we do not know. The nature of dark matter particles remains one of the great unsolved problems in physics. We know that dark matter exists, We can map its distribution with considerable precision, but we do not know what it is made of, how it was formed, or whether it can interact with itself in ways we have not yet detected. The Milky Way, our home, is mostly composed of something we cannot identify. We are, in a very real sense, strangers in our own house, and yet that house is not empty. The Milky Way has companions, smaller galaxies that orbit around it, like moons around a planet. These satellite galaxies range from the relatively large and bright to the small and almost invisible, and their study has become one of the most active areas of modern astronomy. The most prominent satellites are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. They appear as detached patches of the Milky Way, fuzzy glows of light that ancient cultures incorporated into their mythologies and navigation. The large Magellanic Cloud is about 160,000 light-years from us, close enough that we can study its individual stars in detail. It contains roughly 30 billion stars and is home to the Tarantula Nebula, the most active star-forming region in the entire local group of galaxies. For a long time, astronomers assumed that the Magellanic Clouds had been orbiting the Milky Way for billions of years, slowly being pulled closer with each pass. Recent observations, however, suggest a different story. The clouds are moving faster than expected, fast enough that they may not be gravitationally bound to the Milky Way at all. Instead, they might be falling toward us for the first time, newcomers to our galactic neighborhood rather than long-term companions. If this is true, we are witnessing the beginning of a merger that will take billions of years to complete. The Magellanic Clouds will eventually be torn apart by tidal forces, their stars scattered and absorbed into the Milky Way, just as the stars of Gaia Enceladus were absorbed 10 billion years ago. The process has already begun. A long stream of gas called the Magellanic Stream stretches across nearly half the sky, trailing behind the clouds like the tail of a comet. This gas is being stripped away by the gravitational interaction with the Milky Way, and it will eventually fall into our galaxy, providing raw material for future generations of stars. Beyond the Magellanic Clouds, the Milky Way is surrounded by dozens of smaller satellite galaxies. Most of these are dwarf spheroidals, faint collections of old stars held together primarily by dark matter. The Sagittarius dwarf, which we discussed earlier, is one example. Others include the Draco dwarf, the Ursa Minor dwarf, and the Sculptor dwarf, all named for the constellations in which they appear. These galaxies are so faint that many of them were only discovered in the past 2 decades, and surveys continue to find more. The current count of known satellite galaxies is about 60, but simulations of galaxy formation predict that there should be many more, perhaps 100 or more, awaiting discovery. Some of these satellites did not arrive alone. The large Magellanic Cloud, itself a satellite of the Milky Way, appears to have brought at least 6 smaller galaxies along with it, satellites of a satellite. This hierarchy of structure, moons, orbiting planets, orbiting stars, orbiting the galactic center, reflects the fundamental nature of gravity to build nested systems at every scale. Let that settle for a moment. We have traveled far tonight, from the band of light visible to naked eyes, to the invisible structures that govern our galaxy's shape. We have seen stars and black holes, ancient collisions and ongoing mergers, bright companions and the dark ocean in which they swim. But there is one more chapter to this story, a chapter that concerns not where we have been, but where we are going. The Andromeda Galaxy is the nearest large galaxy to the Milky Way. It is visible to the naked eye on clear, dark nights as a faint smudge of light in the constellation Andromeda, and it has been observed since ancient times. When Edwin Hubble measured its distance in 1924 and proved that it was a separate galaxy, it became the first confirmed peer to the Milky Way, another island universe of comparable size and complexity. Andromeda is larger than the Milky Way, containing perhaps 1 trillion stars compared to our 200 billion or so. It is also closer than it used to be. Spectroscopic observations show that Andromeda is moving toward us at about 110 kilometers per second, a speed that will cause it to cover the 2.5 million light-year gap between us in about 4 to 5 billion years. For much of the past century, astronomers have assumed that a collision between the Milky Way and Andromeda was inevitable. Popular accounts have described the merger in dramatic terms, with the two galaxies smashing together, triggering massive bursts of star formation, and eventually combining into a single giant elliptical galaxy nicknamed Milkomeda. The supermassive black holes at the centers of both galaxies would spiral together and coalesce, releasing gravitational waves that would ripple across the cosmos. Recent research, however, has introduced some uncertainty into this prediction. A study published in 2025 used new data from the Gaia satellite and the Hubble Space Telescope to model the future trajectories of the 4 largest galaxies in our local group: the Milky Way, Andromeda, the Triangulum Galaxy, and the Large Magellanic Cloud. The gravitational interactions among these 4 objects are complex, and the outcome depends sensitively on parameters that we cannot measure with perfect precision. The study found that the chance of a merger between the Milky Way and Andromeda in the next 10 billion years is approximately 50%. A head-on collision is unlikely, with less than a 2% probability. In most scenarios that lead to a merger, the galaxies will pass by each other at first, losing energy through gravitational interaction, and then fall back together for a second encounter. But if the first passage is not close enough, they might not merge at all, instead entering a long, complicated dance that could last for billions of additional years. This uncertainty might seem unsatisfying, but there is something honest about it. The future is genuinely unknown, even for galaxies. We can calculate probabilities and run simulations, but the actual outcome depends on initial conditions that we can only estimate. In 10 billion years, our distant descendants, if any exist, will know the answer. For now, we must be content with possibilities. If the merger does occur, it will be nothing like the violent collisions we imagine between solid objects. Galaxies are mostly empty space. The stars within them are separated by such vast distances that even when 2 galaxies interpenetrate completely, individual stellar collisions remain extraordinarily rare. If the Sun were a ping-pong ball, the nearest star would be a pea roughly 680 miles away. Even during a galactic merger, the ping-pong balls rarely hit each other. What does change is the gravitational environment. Stars that have orbited peacefully for billions of years find themselves tugged in new directions, flung into new orbits, sometimes ejected from the merged galaxy entirely. Gas clouds collide and compress, triggering intense bursts of star formation that light up the night sky with young, hot, blue stars. The orderly spiral structures of both galaxies are destroyed, their arms unwound and scattered, their disks puffed up into a featureless, elliptical shape. There is a roughly 12% chance that our solar system would be ejected from the merged galaxy entirely, cast out into intergalactic space. We would not notice any immediate change if this happened. The sun would still shine, the planets would still orbit, and life on Earth, if any still existed at that distant future time, would continue as before. But the night sky would be different. Instead of the familiar band of the Milky Way stretching overhead, we would see only the distant glow of the galaxy we had left behind, receding slowly as we drifted through the cosmic void. In most scenarios, however, the solar system would remain bound to the merged galaxy, simply relocating to a new orbit within the larger structure. The sun, by that point, more than 9 billion years old, would be approaching the end of its life, swelling into a red giant, and eventually shedding its outer layers to become a white dwarf. Life on Earth would have ended long before, when the increasing luminosity of the aging sun made our planet uninhabitable. The merger itself poses no threat to us. It is simply too far in the future to affect anyone currently alive, or their children, or their children's children, for hundreds of millions of generations. There is something peaceful in this knowledge. The collision that may or may not happen will do so long after every concern we currently hold has faded into history. The question of whether the Milky Way will merge with Andromeda is genuinely interesting, a scientific puzzle worth solving for its own sake. But it has no urgency. It asks nothing of us except our wonder. We have come a long way from where we began. The hazy band of light that our ancestors saw stretching across the sky has revealed itself to be something far more complex than they could have imagined. It is a city of hundreds of billions of stars, anchored by a black hole of 4 million solar masses, shaped by collisions that happened before our planet formed, and surrounded by an invisible ocean of dark matter that we can detect only through its gravitational effects. It is ancient and dynamic, stable and evolving, familiar and deeply strange. What does it mean to live in such a place? Perhaps nothing more than what it always meant. We are small creatures on a small world, looking up at a night sky that has inspired wonder for as long as humans have existed. The names and stories change. Galileo's telescope replaces ancient myth. Gaia's data replaces Galileo's sketches. But the fundamental experience remains. We look up, we wonder, and sometimes, in the quiet moments before sleep, we allow ourselves to feel the vastness without needing to understand it completely. The Milky Way will continue turning long after we are gone. The sun will complete many more of its slow orbits around the galactic center. New stars will form in the spiral arms, live out their lives, and die, seeding space with the heavy elements that become planets and moons, and perhaps somewhere, other minds looking up at other night skies. The structures we have discovered, the ancient stellar streams, the dark matter halo, the warped and wobbling disk, will persist and evolve according to laws we are only beginning to understand. And tonight, if the sky is clear where you are, the Milky Way is waiting. It looks the same as it always has, a river of pale light crossing the darkness, asking nothing of you but your attention. The light arriving at your eyes tonight left those distant stars tens of thousands of years ago, before the first cities were built, before writing was invented, when our ancestors were already looking up and wondering what it all meant. They did not know about spiral arms or dark matter or supermassive black holes. They did not know that the Milky Way was one galaxy among billions, that it had consumed other galaxies in the past, or that it might merge with Andromeda in the distant future. And yet, they knew what we know, that the night sky is beautiful, that it dwarfs our concerns, and that there is something restful about contemplating infinity. The ancient Greeks saw spilled milk. The Romans saw a road. The Pawnee of North America saw the path taken by the spirits of the dead. Aboriginal Australians saw a great river in the sky, or the smoke from campfires, or the shape of an emu stretching across the heavens. Every culture that has looked up at the night sky has seen the Milky Way and tried to make sense of it. Every explanation was, in its own way, an attempt to find our place in something too large to fully comprehend. We now know that the light in that band comes from billions of stars in a disc-shaped structure, roughly 100,000 light-years across. We know that we are located in a minor spiral arm, about 27,000 light-years from the center, orbiting a supermassive black hole at a speed of 220 kilometers per second. We know that our galaxy has cannibalized smaller galaxies throughout its history and may be consumed in turn by a larger neighbor billions of years from now. We know that most of its mass is invisible, made of something we have never directly observed. And somehow, knowing all of this does not diminish the wonder. If anything, it enhances it. The more we learn, the more remarkable the Milky Way becomes. It is not simply a river of light or a path for spirits. It is a structure of almost inconceivable complexity, a fossil record of cosmic history, a home for hundreds of billions of stars and whatever worlds orbit around them. To look at it is to look at our own past and our own future, stretching away in both directions beyond the limits of imagination. Picture yourself standing on that surface, if you can. Not the surface of a planet, but a vantage point somehow outside the galaxy, looking back at the whole structure spread out before you like a glowing pinwheel in the darkness. The spiral arms wind outward from the central bar, dotted with clusters of young blue stars and the pink glow of star-forming nebulae. The bulge at the center shines with the accumulated light of billions of ancient suns. Beyond the visible disk, the faint glow of the stellar halo fades into a vast dark matter envelope that extends for hundreds of thousands of light years in every direction. And somewhere in that structure, too small to see from this distance, a yellow star moves in its slow orbit, carrying with it a handful of planets and a species that has only just begun to understand where it lives. There is no urgency here, only the slow, patient turning of worlds. The Milky Way has been here for more than 13 billion years, and it will remain long after every word of this has been forgotten. The problems that weigh on you tonight, whatever they may be, are the concerns of a moment. The stars have their own timescales, measured in millions and billions of years, and from their perspective, the entire history of human civilization is a flash, a brief flicker in the long story of the cosmos. Sometimes the universe is simply showing off. The structures we have discussed tonight, the spiral arms and the central bar, the ancient stellar streams and the dark matter halo, the satellite galaxies falling in like slow-motion rain. All of this exists without any need for our observation or understanding. The Milky Way was turning before the first living cell appeared on Earth. It will continue turning after the last star burns out. We are witnesses to something that does not require witnesses, participants in a story that does not need our participation. And there is something liberating in that knowledge. You do not need to remember all of this. You do not need to hold in your mind the mass of the supermassive black hole, or the date of the Gaia sausage Enceladus collision, or the probability of a merger with Andromeda. These are details, interesting details, but details nonetheless. What matters is the larger truth that underlies them, that we live in a vast, old, beautiful galaxy, shaped by forces we are only beginning to understand, and that looking up at the night sky connects us to something far larger than ourselves. The Gaia satellite that revealed so much of this history is still operating, still scanning the sky, still adding to our map of the galaxy. Future missions will reveal more. The mysteries that remain, the nature of dark matter, the exact history of our galaxy's formation, the ultimate fate of the Milky Way and Andromeda will be solved by minds not yet born, using instruments not yet invented. The story is not finished. It never will be finished. Each answer leads to new questions, and each question leads deeper into the mystery. But you do not need to follow those questions tonight. Tonight, you can rest. The band of light that crosses the sky has been there since before humans existed, and it will be there long after we are gone. It has witnessed everything that has ever happened on Earth, every birth and death, every joy and sorrow, every triumph and tragedy. It asks nothing of us, demands nothing of us, expects nothing of us. It simply is, a river of ancient light flowing silently through the darkness. The stars that make up that light have their own stories, each one a nuclear furnace converting hydrogen into heavier elements, living out lives that span millions or billions of years. Some of them have planets. Some of those planets may have life. We do not know, not yet, but the possibility is there, shimmering in that band of light, waiting to be discovered by future generations who will look up with the same wonder that you feel tonight. Our sun is one of those stars. Our Earth is one of those planets. We are not separate from the Milky Way, but part of it, atoms of a larger body, thoughts in a larger mind. The calcium in your bones was forged in the core of a star that exploded before the sun was born. The iron in your blood came from a supernova that scattered its elements across space billions of years ago. You are, quite literally, made of stardust, a temporary arrangement of matter that was once inside other stars in other parts of this galaxy. That thought can be overwhelming if you let it, or it can be comforting. You are not an observer of the Milky Way, looking at something distant and separate. You are part of it, a small piece of the galaxy looking back at itself, trying to understand its own nature. Every question you ask about the Milky Way is, in a sense, a question the galaxy is asking about itself. And so we come to the end of our journey, though the journey never really ends. The Milky Way will keep turning, the stars will keep shining, the invisible dark matter will keep holding everything together. Andromeda will keep approaching slowly across the millions of light years that separate us. New satellites will fall in and be consumed. New stars will form in the spiral arms and die and scatter their elements across space. The story will continue, with or without us. Tonight, though, let the story pause. Let the slow rotation of the galaxy become a kind of lullaby, a rhythm too vast to hear, but somehow felt in the quiet moments before sleep. The stars are not going anywhere. The mysteries will wait until morning, or until next year, or until the next generation takes up the work. There is nothing more you need to do tonight. The Milky Way has been turning for 13 billion years. It will turn for billions more. And in all that immense sweep of time, there is this one moment, this one night, when you looked up and wondered about your place in the cosmos. That moment matters, not because it changes anything, but because it is part of the story too. You are part of the story. You always were. Let your eyes grow heavy. Let your thoughts drift. The galaxy is still there, spinning slowly in the darkness, holding its billions of stars in their long orbits, waiting patiently for whatever comes next. It has been waiting for a very long time. It can wait a little longer. And so it turns, as it has for billions of years, asking nothing of us but our wonder. Good night.